Anybody still missing, or should I just start?
I'm not here.
Okay, I got that, so I start. Okay, so we'll talk about way computers calculate wrong, which doesn't help you. The world dies if we have this situation, but anyway, I talk about it anyway. So anybody of you might be, not many, but somehow maybe old enough to know about the year 2000 problem. And that's like the issue, how many digits do we need to express a year? And everybody told, of course, 2, because we are lazy to write, and that's what we program. And then we had like a $1 billion business to fix everything, and we basically did that. So we survived until now, so that's good. But I think this is a more general problem. It's not just about this year issue. So when we talk about integers, integral numbers, you use that. What kind of integers do you use? Like who uses Perl 5 or Perl 6? I don't know, maybe you just use with what comes out of the box. So we'll look into that. But you know, we are talking here in the Perl community, and there's another language than Perl 5 and Perl 6 that's legitimate. And that's what people have decided to use for writing Perl itself. And this language is more useful for exploring this kind of issue because it's more direct, but we'll get to Perl for the rest of the talk. But this, I think, makes it clearer. So we take like an integer, don't have to count it, but it's 2 to the power of 9, 2 times 10 to the power of 9. Then we add it to itself, we multiply it with itself, and we use a certain operating system and a certain compiler. So it's this computer and GCC, and it's Linux and 64-bit, but anyway, that's what we have. What do you think will be the outcome? Any ideas? If you take 2 billions and add it to itself or multiply it with itself, let's see. Of course, it's negative, yeah? And this is also something negative. Yeah? So it's just wrong. So, yeah, most of you know about this, but it's something we just don't have to only know, but we have to deal with it because we often tend to not care, and then we work with it anyway. So I want to make sensible and see how we deal with it properly. So we see, the idea is we have ranges. So it goes from the power 2 to the power of 31 to 2 to the power of 31 minus 1. Yeah? And it's something like that. We always have, that's the machine integers. And then when it overflows, it does something weird for the moment. So we do it in Perl 5. So what do you think when we do this in Perl 5? Same machine, same, like it's 524, so I'm up to date. Yeah, what do you think we get here? Something right or something wrong?
Floating point.
So?
I'm going to guess floating point.
No, just what was. Okay. So why? Because it uses 64-bit integers.
Yeah.
And so now we go larger number. Yeah. So I just put something that fits into 64-bit signed integer. Yeah. And we try this. Let's see. And you said it right. It goes to floating point. So this one is still right because it seems to go to unsigned integer. Yeah. This one is not quite right, but yeah, that's what we have. Okay. So we try now. We want to force it to use integers. Yeah. So we use this use integer, and then we run it like this. And now let's see what we get now. So it's something negative. Yeah. So it doesn't go to floating point. It has 64-bit integers, so it only sees this in the whole world, and everything else is impossible. And then it just goes to this negative with itself. Okay. Now we try Perl 6. Yeah. So what do you think we get in Perl 6?
Many digits.
Correct answer.
Yeah. Just words. just works. It's nothing new. Of course, Perl 6 is new, but Lisp has done it since the 60s or so. So the idea is not quite new, but I think it's good that Perl 6 does it. But you can have your own opinion. We just saw now 3 different patterns. Yeah? But now let's see, we can control how Perl 6 behaves. So now we tell Perl 6 to use ints with the small I. That's very important. The small I is kind of the special case, yeah? Because that's the machine integer. Okay? So there we get the weird result again. So the small int is something faster. Okay? So we have different behaviors. We just get the wrong result, whatever it is. In C, in Java, I can promise you it's also wrong. Yeah. In Perl 5, if we use explicit small int, and in Perl 6 also. Then in Perl 5, we have this whatever an intermediate kind of behavior. It falls back to floating point. It's not very wrong, but it's not exact. Yeah. And Perl 6 just does it mathematically right. Yeah. And now what would you prefer? Okay? So, the thing is we should see that we control, we have an idea what we want, but we want to control that it does what we want. Yeah? And so we should understand this. I think, you know, we have had modular arithmetic as part of the previous talks. And so basically we have to understand what this plus, minus, and times means. And all of you who know modular arithmetic is clear, but for all the others it's clear as well. It's this. Everybody knows this, and if we have 11 and then we add 11, of course we get 22, but if we are English speaking, which I am now, then there is no 22 on the clock, it's just 10. Okay? And if you multiply, you just enhance the idea, and that works for multiplication as well. So you're always in the range from 1 to 12, and whatever you do, you never do it. And it's like that. You just have a watch with not 12 digits, but with 2 to the power of 64 digits. Yeah? Little bit. I don't have enough pixels to express that, but you can imagine. Okay? And then it's just that. Or 32 if you are in, depending on what kind of integer you use. Yeah? So we can understand this, we can rebuild the, you know, we have the same integers in Perl 6, and we can rebuild the broken ones, even the one with 32 bits, because it's less writing here. I would need to write more digits to simulate the 64-bit, yeah? So we take this modulus, that's 2 to the power of 32, and we have the half of it, that's the limit, because we have like from greater or equal minus the limit and less than plus the limit. So we have more negative than positive, whatever. Yeah? And so we take this percent modulus, and we could look up in the documentation where this actually lands in terms of range, but we could say we just don't care, this should just work, and I can port this to any other programming language, no matter what percent has as a range. So it could be something between minus limit and plus limit. And I deal with it if it's minus modulus plus, I deal with it if it's too negative, I add 1, if it's too positive, I subtract 1, and then I'm in the desired range. Yeah? So that's that. And then we have a plus, it's normal addition, and we just normalize with this function that we saw on the previous page. Yeah, and the other one is the same. Division is a different story, because division, I could do a talk by itself, we just skip that for today, yeah? And then we revisit this quiz, yeah? Now we are again in the number range that we had on the first slide with the int of C, or int of Java would be the same. So what do you think we get now? These again. Trust me, it's the same numbers, but I did calculate with this program, yeah? I didn't just copy-paste it from the other one. Okay? So, we see this int has a weakness. It suddenly overflows with modular arithmetic. And I would say like 30 years ago, when we had to tune the CPU, and we had like 1 megahertz of CPU, and we had like 8 kilobytes of RAM, then this was really cool, because we were extremely efficient in using our hardware. And now we still use this, but people are no longer aware of bits and bytes. Yeah, we have like frameworks and Catalyst and or whatever, Java Enterprise Edition, and this thing is not in our view anymore. Yeah, but we still in some programming languages, or at least some ways of using them, we still have this thing, and we have this bit optimization in an area where we don't need it and we don't want it. Yeah. So this thing does a silent overflow. It doesn't throw an exception. There's another behavior which I can't find in Perl, but in Clojure you have it. You can make it throw an exception when it overflows. But it's not so useful either, because you still have this situation, you run it, you test it, everything goes fine because you tested 1, 2, 3, 4, 5. Yeah? And then you run it in production, goes very well, but then you have the end year processing, and then suddenly you break it. And nobody knows why, because the exception occurs somewhere totally different where the actual bug occurred. Okay, so we just looked a little bit more on this floating point thing. It's of some relevance because all of us have to deal, if we like it or not, with JavaScript. And JavaScript, at least to my knowledge, is using floating point all the time. Yeah? And then we should understand how we can express integers with floating point just for the sake of JavaScript, and also because Perl 5 does it. So we can see we have 64 bits integer, and when that overflows, we fall back to 64-bit floating point. Yeah? And it can go right or wrong, you can be lucky or not, so we should know, not just guess. Yeah? And I did explore it, so I wrote a blog post maybe about it, at least I did this some time ago. So the floating point number looks like this, as a general idea. We have a sign, then we have a mantissa, and we have an exponent to the, which is based on base 2. Yeah? And we have certain bits, so we have 1 bit to express the sign, we have 52 bits to express the mantissa, and then we have 11 bits for this exponent, and then we have some special ways to express plus 0, minus 0, plus infinity, not a number, and all these things, yeah? But it's kind of doesn't get in the way for the time being, because it's just taking out a few spots of this range, and so it works. So then we can look into the extrinsics and look at the documentation. We can try it out with a C program, which is really going to the raw iron to see where it's going. Or we can look up on the internet and we all get the same results. So we are good if we are inclusive of the boundaries from minus 2 to the power of 53 to plus 2 to the power of 53. It's 1 more than we would expect, because the 1 in the mantissa, it always starts with 1 that we get for free. We don't have to store it. Yeah? So therefore it's like that. Okay? And if we are outside the range, sometimes we're good, sometimes not. But then it's getting weird. So if we write JavaScript and we know for sure that all the numbers are within that range, then probably it's okay. So we lose precision in this case, that's the point. So how do we address it? And the way we address it is, I would recommend to use begin when it's necessary. Yeah? And we can think twice about the values. It's always good to think what's happening in our application and to understand it. But you have to think of the intermediate results, because you say, okay, I get something out that fits very well in the machine integer. Yeah? And we put something into it, but we do a multiplication and then some weird thing, and then in the intermediate results we get mistakes, and then the wrong end result is wrong anyway, unless we're lucky that 2 bugs cancel each other, which happens, which is weird, because then testing and production behave differently. But anyway, you should either investigate the whole thing and really know what's going on there, or just use the begin, or do both. That's the best. Okay, so now we can do that in Perl 5. Actually, it's very easy. It's not even more to write. We just use begin, and yeah, then it's like this, and we are good. No big deal, just 1 line. Okay, so the good news is, so Perl 6 does it right anyway, out of the box, no problem. Perl 5, this big int is just one line and then it does it right. What is really cool, I mean for us it's no coolness, it's clear, but if you look at Java or C or so, if you use something like begin, then suddenly you can't write plus, minus and times anymore, you have to write weird multiply, call this function and this, and then you see a formula like this, and you don't understand what it means. And that's a serious issue because you create bugs, you don't read it like this. And here we can just write what we mean. So I think it's very important, but it's just good news. And I would say, but it's of course opinionated, but my opinion, we can usually afford the performance overhead. Of course, if we do this thing where we do this calculation for these number theoretic things, then of course the overhead of begin does cost us something. But usually I would say we can just afford it and we lose performance on the database and on the web latency and other areas. Okay, and we cannot afford weird or wrong results usually. Yeah? So if we do like accounts and then the money is suddenly minus and when we add more to the account or so, no. Yeah? At least if it's my account, I don't like that. And I guess you don't either. Okay. There is a point, if you really want to go into this, it's actually not so hard to recognize this overflow situation. You have to look at the bits of the input and the bits of the output, and then you can do some combination, and then you can find out this would overflow. I don't think we should do this in application code. It's just not our task. Yeah? But just for the interest, and if you really need to push it to the bit performance, you could. Okay. So let's see where we are. We can turn this thing on and off very easily. So we can just use begin and then use no of it. Yeah? And then we say use integer and use no. So we can turn it off and on. And then when it's turned on, it uses that. And when it's turned off, it goes the normal way again. It's not, maybe not how we would design it now, but that's what it is. We can use it. Okay. You can scope it in blocks also. And in Perl 6, it's like we can control it with a type. So we call it big int. Yeah? And by that we say this one is meant to be this type. It's more or less like in most other languages, so it's, I guess, easy. And this one, if you really go. So I guess we come to the next issue. It's floating point arithmetic. Who of you has used floating point arithmetic in the last year? Okay, so it's real stuff. I thought it's more for amusement, but anyway, I tell you anyway. So we have this example. We take a 1, then we divide it by something, then we add 1, subtract 1 again, then we multiply by something, yeah? And then we get something. What do you think we get? Zero, yeah? Of course. Anybody know why?
There's no fractional parts either.
No, it's well. That's a question how the print works. I mean that depends on, but it doesn't really bother us. But in the end, we lose something here. Yeah. So let's see. The point is we use something called double or floating point, but it's basically 64-bit floating point number. And it has a certain number of significant digits. We already saw it was like 53, yeah? And only 52 we need to store the one we get for free, yeah? And not more, yeah? And so if we put something with 20 digits after the decimal point and then add 1, then we would need 22 digits to express this, yeah? And that's beyond what's possible with this number, yeah? So, we need to see when we deal with floating point, I can't give such an easy answer here because it's just a more involved issue. So I guess the point is we really need to know what we are doing. Yeah. And if we do something that uses a lot of double, then I think it's a good idea to get somebody who knows numerical math. There are people who really specialize in this and that's their task and they know it and get their knowledge to deal with it. Or if it's more like something we can do, then but spend some time to understand what's going on there and not just try and hope it's going well in the end of year processing. There is an idea which I would recommend when you use these floating point numbers. Try to think if we really need it. So we can think, is our application really possible to think in integers, of course big integers, yeah? So the typical example is when we have money. We can use double because it's $5.36, yeah? But we could as well say it's 536 cents, and then it's an integer. There is a big problem with this, and it's a serious one. You have like a program, and you have money amount variables, and then some people think it's like dollars, and some think it's cents. Yeah? And then you add something, and this all integers, and then suddenly you have this factor of 100 getting it wrong. So you really need to name it explicitly, at least, that it's money in cents, or something like that. Serious, just spend the extra bits to write it down. But I think it's a good idea. So the other approach is to use rational numbers. Yeah? It's like the fractions with some integer divided by some integer, which we learn in school, 5th grade or so, or 6th grade or whatever. Yeah? And they are nice. Yeah, they're mathematically nice, they behave well, and they don't have rounding errors as long as we only divide, multiply, and add in these things. Yeah, if we take square roots, then it's another issue, but we don't talk square roots today, so it's good. And the problem is, though, they get huge and slow. Yeah, but for these simple examples, they just work. So we see this is Perl 5 again. Yeah, and we use big red. Let's just give to the numbers. If you use that, let's see what we get there. We can even write this 1 in 20. It doesn't bother that it looks like a floating point, but it understands it correctly. So here we get fractions, and the end result is correct. And that these are a little bit biggish, doesn't matter, yeah? Because it's not a long calculation. And if we use Perl 6, it's called RUT. Yeah? So let's try this. What do you think we get here? Sorry?
I would hope one, the correct answer.
Yeah, I would hope too, but it isn't. You get a failure here. And the reason is this RUT in Perl 6, they just took serious the fact that these rational numbers tend to get huge in top and bottom, and you just blow up your memory. So this one has just an unsigned integer as the bottom, the denominator. And therefore, this is not fitting in a 64-bit unsigned integer, so it fails in this line. So, yeah, but it's not that bad as we think. We can just, that's the explanation. So, we can just use fat red instead. Yeah? And fat red just uses arbitrary integers, both bottom and top. And with that way, we can try it again. Yeah. Just works. It just expresses them in a different way, but it doesn't matter. It's just the same as the Perl 5 one. Yeah? So, that's a good way. The drawback is the LCM problem. So, whatever operation you do, if you multiply the tops and the bottoms, yeah, and you just get something that's twice as long. Of course, you can cancel out a little bit, but usually the GCD is nothing, so it's just you cancel out 2 or 5 or something like that, and it's still getting almost double. And if you add, then you have to take the least common multiple of the bottoms, and then multiply with something, and then add it, and then maybe cancel out something, but usually you can't cancel out anything series there, so it even multiplies there. So you double with each operation both parts. And if you double, your memory usage grows exponentially, yeah, by the number of steps, your calculation. And if you do like a matrix operation with 20 times 20 matrices, yeah, maybe it works, but 40 times 40, no. You see? So this is correct, but not really useful for big calculations. I can't help it, it's like that. So think about, maybe it helps, maybe not, but you have to keep this in mind. And usually if you do long calculation, it will blow up. So there is something like long decimal, big float, or whatever. That's like number with a fractional representation which represents some floating point number. There's different ways, but that gives you something like float, but with a more larger precision. Yeah, and then you can control the precision explicitly. You can use that, but it's slower than floating point, because a floating point is in hardware, so you can do like in very few CPU cycles the whole operation, and this one does a lot of stuff. So let's see, we can do that in Perl 5, and then we look at it. So let's see, I just did it naively, and we get out something right, so this needs to work. And the reason is basically it takes into account how many digits we have, and then we have, when we add, multiply, and subtract, there is a rule how we can expand or change the number of digits and still remain within what we have. So it's not necessary to explicitly control, but then with multiplication we double the length, of course. And that can be an issue or not, but usually is okay because the addition doesn't hurt us so much. So yeah, but as soon as you divide, then you need to explicitly control precision. So there is something, this is a beast. Yeah, you can use it, but if you do more things with it, then you have more parameters to turn on, and you can't ignore them all the time. So you have to deal with something that I talked about a little bit yesterday, this kind of thing, yeah, rounding, and you have to control that, you have to control how much precision you want, and yeah, so I guess it's in the end of the day a little bit more work, but, and the other thing is it's not usually exact. Yeah, but you control the precision, and that's probably good enough. And in some cases you can be exact, like the example that we had here. So yeah, I think it's a good way, but you need knowledge. Then concerning Perl 6, I didn't find any way to do this in Perl 6. So maybe it is possible, but now we know that it's possible. We just use the Perl 5 from Perl 6, and then there. So there's another approach. I just touch it here. I haven't used it, and I haven't seen anything in Perl about it, but this doesn't mean that it doesn't exist. This is using intervals. So you use like any kind of numeric type to express numbers, but when you do any operation that is not exact, yeah? For example, you divide, or you do the square root, or you do something, but you need to round for the sake of the precision. Yeah, you just take the lower and the upper rounded value. You round both ways, and you take both of them, and you say, okay, whatever my result is for sure between these two values. Yeah, and then of course you put in two values into the calculation, and if you have more parameters, then each of them is 2. But you can do the math, and basically the libraries that do this know the math, and they know how to deal with it, and then you have in the end an interval, and then you know, okay, if my interval is from minus 5,000 to plus 6,000, probably my calculation is crap, yeah? But if you see it's from 5,000 to 5,000.001, probably it's it's a result we can use because it guarantees this. Yeah, it's a way to go, but I don't know anything how to do it in Perl. It's just an abstract knowledge, and I know there's libraries in C, and probably the way to do is write wrappers around that. Okay, so something based on GMP, I think. So there's another issue that's also concerning floating point, and it looks so trivial that we can hardly understand it unless we look a little bit further. So we take 0.2. It's a very nice number, it's easy to express. And then we print it. Yeah? And we print it, %A, you don't need to know it, I just tell you. It prints it, the floating point representation, but in hex. Yeah? So it does exactly its internal presentation shown in a human readable way. Yeah? And then let's look what we get. So the T is 0.2, that's the same. And then actually what it internally has is 1.99999. Okay, but it's not this 1.999 which is actually 2, because we are a hex system and the 9 is not, yeah? So that would be, this one would be almost 2, yeah? But we are not there. So this is really something periodic, yeah? We have infinite number of digits, we need to express it. And why is that? In decimal system, we can express certain fractions very well. Yeah, it's like 1/5, 1/10, 125, whatever. So if the denominator is some product of 2's and 5's, then it goes well because we just take a power of 10 that is big enough, and then it's divisible by that, and then it works out. And so that's what they have in common. But now we are in a binary system. So there we need a power of 2, and needs to be divided, you need to create a big power of 2, and that needs to be divisible by the denominator. And the only way to have it is if the denominator is a power of 2. And so 0.2 is 1/5, and so no power of 2 is divisible by that, right? Yeah. So we can see if we go here, if you know how you did these, you multiply it by 16, yeah, and then you subtract one of it, and then you get like 1/8, yeah, and that is then you divide it by 15, and then you get 24 divided by 50, that is 8. Divided by 5, and then you see it times 2 to the power of -3, and then you are 1/5. Yeah? So you can do the same kind of thing. So in decimal system we have the same issue with 1/3 and 1/7, but they don't hurt us as much because the 1/10 are more common to use because we use decimal system. So the point is double uses the binary system, and therefore it has this screw with the decimal system that we use in our lives. So there we got it. And now the question is how we deal with this. And then we have to think, is the decimal system part of our business logic? Sometimes it is. Sometimes it isn't. Sometimes it's just, yeah, okay, the 0.2 is just as likely as the 1/7, then it doesn't matter. Yeah? So if we do financial calculation, probably decimal system is part of our world. If we do scientific calculation, probably it isn't. But you have to think about that. And then again, use integers, and you're good. Or use this long decimal or whatever that's exact to that area. So the Perl 5 big float name is a little bit confusing, but that would work in this case. And just the last point, never, ever, ever, ever use double to express money. Okay? Thank you. Questions? Yeah.
Not really a question, but a remark regarding the overflow on native int in Perl 6.
Yes.
we discussed this, and basically Jonathan decided that we're not going to do any overflow checks on natives in Perl 6 because actually a lot of applications, specific cryptography applications, actually depend on it. And so
I think it's fair enough because if you use the int, the low-level int, then you are in a dangerous world without safety, and you should know what you're doing. The only thing that I would criticize is the name is too short. They should have chosen a name that is this long to say you are now using something.
Don't use me, please.
Sorry? Yeah, but you know now. Any other questions? Yeah.
What happens when you use a big int and then use integer? Next slide. In Perl 5.
If you use a big int and then an integer.
And use big int and then next time use integer.
Then I think when you combine it, it goes, that's a big issue what it does there, but it should go to the bigger one when you combine it. I think it does it. So the examples that we did here were actually, some of them were like that, where you had a big integer and then you added something to it, that was the one is not necessarily a big integer, and then it did the right thing. Yeah?
One question which actually Stefan already answered to me,
Yeah.
but which may be interesting for the public.
Yeah.
You showed that one example which failed with native values in Perl 5, but didn't in Perl 6.
Yeah.
So I was wondering what was happening if you use inline Perl 6 and Perl 5 and then do that.
That's an interesting question, but maybe you know the answer, I don't. So maybe you can...
Stefan knows.
Stefan knows the answer, okay.
Well, I only know this because I tried. But this whole bridge thing works by using Perl 5 C code access embedding interface. So there's a lot of C data types involved. And on the Perl 5 side, you have IVs, which are integer values, which are the integer type that you gave it when compiling Perl 5. So it's usually a native integer. And we use that as the target type in native call, and it detects, okay, I have this huge integer, like 73 bits, and I only have 64 bits of space, so it errors out. I could probably make it somehow work by wrapping the actual int objects in Perl 6 and passing those to Perl 5, maybe with some operator overloading. I just wonder if it's really worth it.
I think it is, but...
If you can give me some real world example where you actually would want to use it, then I may implement it.
Okay.
I see a lightning talk.
Okay. So, thank you so much.